today's lecture. Although I do everything on the Blackboard, I sort of prepared slides. So you're welcome to download them. They're a little bit hidden on my homepage. So what you should do is you first find my homepage, which is not very difficult. You just Google my name here. And then you find my TU homepage. Yes, but there's some delay, so we can do that as well. But they're already there, so you can get it now if you want. And then you go to my homepage. And there's a little link called Student Info. And if you click on this one, Student Info, you'll find the IHP lectures. Number 1 and number 2 as PDFs, and you can have a look. Good. Okay, I think it's appropriate to give the definition of a rough path again. It's sort of central. So, rough path. So you start with a path, given a path x you may think alpha Helder, but I'll put this down in a second. You postulate some sort of second order increments and as a matter of notation, I hope it's clear, but someone asked me yesterday, so let me emphasize it. When I look at the vector valued path, something like this here just means the vector increment. So this is xr minus xs. Okay. Of course, it's not true for this matchbolt xst, because this one does not behave in this additive fashion. Instead, we have seen Chen's rule that tells us what happens. And in fact, this is one of the axioms we're going to put down here in a second. So, such that there's this analytic condition, Ana alpha, which basically says that our path is alpha Helder. Right. I mean, if you look up my book with Martin or any other lecture notes, of course, this is spelled out, and you can write it as there's a constant here, and you want this uniformly over S and T in your interval of consideration. But this is good enough for Blackboard. And then, of course, the same for the second order increments. T minus S 2 alpha. And alpha will be between a third and a half. And as far as the deterministic theory goes, you can take alpha equals 1/2. Right? It's in this regime here. If you apply it to Brownian motion, you will have typically alpha 1/2 minus a little bit. Yeah? This is the analytic condition, and then there's the algebraic condition that ties these x and bold x together. And the first one is this Chen condition. And basically it's, if you look at 3 times S, T, and U, this is how you batch together these higher order increments. And then you have a chain rule, which you may or may not want, depending if you use Stratonovich or if you have Stratonovich situations in mind, or rather Ito. So there's this chain rule. And if you think about it, basically you believe in a product rule without any second order correction. This translates this translates exactly in a condition on the symmetric part here. So the symmetric part of such an increment. Okay. Okay, these are the three conditions, and now you can wrap them up in a definition here. So here we go. Definition: such a pair such that Ana alpha for alpha in and this chain condition so again a pair X exposed such that the analytic condition holds and the chain relation holds is called a rough path. Is called a weak alpha Helder rough path. Okay. Why weak? Well, you can come from a different angle and say, I only want to look at smooth path, but then I look at the completion in some rough path metric that gives me a richer space. And these would, I mean, this is the terminology that is standard. These are the genuine rough paths. And the way I define it, they were called weak rough paths. In any case, it's just terminology, not very important for us here. Now, if you impose the chain rule in addition, then you call it geometric rough path. If also impose the chain rule, then it's called a geometric. Or if you want to be completely rigorous, a weak alpha Helder geometric rough path. So geometric rough path. Okay, now I said it in the last 3 minutes yesterday. Rough paths, the way I defined them, are really paths. They're not some weird pairs of, path and 2-parameter objects. And it's really a consequence of Chen. And let me point this out again here. And let me move over. Oops. So we're heading towards a geometric view. On rough path spaces. So what Chen really says is, if you use the language introduced yesterday, the tensor algebra, in this case the level 2 truncated tensor algebra with the tensor product, etc., then So if you want, this takes values in this. Step 2, truncated tensor algebra. And if you read this chain condition, it actually says nothing else than xst, which is 1xst right? I mean, if you take this bare-handed point of view, there's no need to write a silly 1 here all the time. But if you take a geometric point of view, it's natural that you put in the scalar 1 as we did yesterday. Yeah. So what you see is a rough path is really a path, and when you want to work out these increments, you just get them from chance relation. So in that sense, chance relation is a tautology when you come from this point of view. Right. Now, the chain rule says something else, namely, it tells us something about the state space. So yesterday I introduced the space G2 as the image of all signatures of smooth paths, right? And the chain rule effectively says that you take values in the space G2. Okay, and at last, let's give a clean view on the analytic condition. And to this end, I hope many of you will know the Carnot-Caratidori metric. And I pointed out yesterday the Subriemannian structure on G2. So there's clearly a Carnot-Caratidori metric. And since we're on a group, you only need the Carnot-Caratidori norm and then use the group operation to turn it into left invariant metric. So at last, so I now consider geometric graph paths. Yeah? All right. And so I don't have the time to go in much detail here, but at least I want to write it down here. So this distance here is as follows. If you give me two elements, G and H in G2, then the first thing is I play it back to the Carnot-Caratidori norm, which I haven't defined yet, but I will do it down here. So the Carnot-Caratidori norm is simply the infimum of the length of, let's see, x is okay, x or x is smooth and S2 of x is G. So remember, S2 of x was simply the step 2 signature. That means you take x, compute the iterate integrals of x, and together they give you an element in G2. Okay. So now this is a pretty picture. It means a weak alpha-Helder geometric graph path is no weird object after all. It's simply an alpha-Helder continuous path in a certain Lie group, which is alpha-Helder with respect to the Carnot metric that's well defined on this Lie group. So it's a quite pleasant concrete object. Okay. So since there's an obvious Subriemannian structure here, this gives you a natural way to approximate rough paths. In the same way as the natural approximation of a curve in RD would be to look at some partition of your time interval and then you make little straight lines. You can do the same in the group, but instead of straight lines, you use geodesics in the group. So there's another benefit of this discussion here, which means you can quantify the geometric graph paths as limits of smooth paths. And I want to make this a proper theorem. I mean, this is really where much of the story comes from. You can do everything for smooth paths, but you look for uniform estimates that are rich enough that you pick up interesting stuff in the limit. And so this theorem here will quantify that. So here's a theorem. For every weak geometric alpha-Helder rough paths X, there exists a sequence of smooth d-dimensional paths smooth. I mean, the construction will naturally give them to you as piecewise let's say piecewise smooth, but then there are silly tricks like whenever you concatenate two smooth segments, you just slow down before you see the kink and then you start again, so you can make them smooth, I mean, in a very silly, obvious way, such that, okay, S2 xn converges to x. Right. That means you have convergence of your path and you have convergence of the iterated integrals to this sort of postulated second order information of your rough path. And this you want to happen uniformly, but that's not enough. You also want the uniform alpha-Helder bounds. With uniform alpha, respectively, 2 alpha Helder bounds. So in other words, the estimates that are imposed in this analytic condition here, I want them to hold uniformly for these approximations. Yeah? Okay. The proof, I mean, again, let's not worry too much about the smoothness here. Smooth just means smooth enough that here you're back to calculus. So smooth can be rectifiable. But then if you approximate this once you have xn and they're rectifiable, you can do a second approximation step and replace them by smooth ones. So it's true either way. So, but if you go for rectifiable, so then the proof is almost obvious if you know a little bit of Subriemannian geometry. Namely, you think of x as a path in, this is your x with values in G2. And you do the obvious thing. You look at some partition here, right? And the mesh should go to, I mean, you look at the sequence of partitions, and the mesh, of course, should go to 0. And what you do in between, if you use geodesics here. In G2. Right? And so now you see why I didn't want to keep smooth here. I absolutely do not want to get into the business of discussing smoothness of geodesics. I mean, here you're in a level, in the step 2 nilpotent group, there it's okay, but you can do this in level n, and these are difficult questions, and as far as rough paths are concerned, you don't care. So this is the idea of proof. Okay. And if you set it up right, the proof is very much the same as an elementary exercise in analysis. If you give me some alpha Hölder path, scalar valued if you want, and then you ask your students to prove that piecewise linear approximations will converge uniformly with uniform alpha Hölder bounds, that's very easy. Right? The proof here is the same, once you set it up in the right way. Okay. I mentioned it, but I wanted to point it out again. If you try to do rough path theory, not in this regime alpha between a third and a half, but you want to do something very rough where alpha is, I don't know, 0.001, then it's okay. You just need more levels. I mean, in the regime between a third and a half, you just need 2 levels, and the relation here is that the number of levels here 2 is the integer part of 1 over alpha. And if you take this alpha here, the integer part is plainly 2. This is why you get away with 2 iterate integrals, or the second level iterate integrals. You can tell the same story for any alpha, but then you need, integer part 1 over alpha, and perhaps, could be many. But the definition of a geometric graph path is still very clean. You just have to work not in G2, but you work in Gn, which is the step n nilpotent free group, sitting in the truncated tensor algebra, and you're good to go. So these are just definitions, but what do you do with this stuff? Rough integration is the first thing you want to do with it. And so at this moment, we take a step back from this geometric point of view, because what comes now is completely elementary. And I would argue that rough integration is simpler than stochastic integration, because it's a piece of analysis, 4 pages, self-contained, and everything is done. Okay. So, rough integration. Okay, let's be humble and let's consider the problem of integrating a so-called one form. That means I consider as integrand y equals f of x. Right? And then I want to integrate against x. Now we already know this notation here. There's a reason why I introduced y, so you'll see in a minute. We already know this can't work. Because if I just write x here, I don't have enough information to make up my mind. Right? There could be Ito, Stradonovich, God knows. So as you expect, the right thing to do will be to use the rough path here. which contains the second order information. Okay, and what is your hope here? So this is your hope that it will be some Riemann-Stieltjes type limit of, well, you could take ys x s t. Well, this would be the usual left point Riemann-Stieltjes approximation. And of course, you know that thanks to probabilistic cancellations, in the Brown motion case, it will work. It will give you the Ito, but it's not very robust. So a better thing is to feed in the second order information that you have in your hand. And I mean, morally, you just, instead of freezing the integrand over the intervals of your partition, you just say, well, let me use Taylor's theorem and look at the linear approximation here. So that will get me something out that's a small scale linear in x, and then I integrate against x, which is exactly the information that's encoded by this matbold x. So it's quite natural that you try something like this, where you introduce y prime as just d f x. Yeah? So even if you wanted to do Riemann-Stieltjes integration on a computer, you may want to prefer this approximation to this one, because this one will have a better rate of convergence. Right? So, I mean, from a numerical point of view, it's certainly sensible. And now, it's a theorem that this is not hope, but true. So this is true. Yeah, I mean, what I'm summing here, I sum over all little STs in some partition here, and then I take the mesh of the partitions down to 0. That's my notation. Yeah. Pardon? Yes? Well, first I need to show this exists, and then I can give it a name, right? So this is the theorem, the existence of the limits, and then, yeah. So, okay, good. Right. So from an analytical point of view, I mean, we pointed out yesterday that sort of stochastic integration is, from a Schwarz distribution point of view, just not possible. It's ill-posed. But here, in effect, we overcome this problem. We are able to multiply f of x with x dot. Right? And the price we've paid to do so is that we have imposed the meaning of x against dx. We just postulated it. Then we feed it in, and that robustifies the situation. Okay. What's good about this rough integral? It is robust. So here's another fact. This rough integral f of x dx depends continuously on x with respect to a so-called rough path metric. So the way you measure the distance between two rough paths, so if, is simply you look at the underlying path, and this you just measure in alpha Helder sense. Okay, so this is the sup of x st minus x. Okay. And just for safety, you may want to make sure that the starting point is also nearby, plus two alpha. So this one is more interesting, but again, I mean, the sup, of course, runs over all st in your time horizon 0 capital T. And here, It looks pretty much the same. But now with 2 alpha. Okay? So if you compare this with stochastic integration, there's no such result in stochastic integration theory. I mean, you may have a probabilistic statement that tells you if you look at piecewise linear approximations, it will converge to the Stratonovich integral, but if you do it differently, it may not. Here, it's a purely deterministic statement. Okay? So if you want to understand convergence properties of stochastic integrals, what you have to check is that these guys do the right thing, and then you're in business. Okay? I'll come back to this.
What's the connection with Fermat?
Well, I mean, Fermat is essentially, in Fermat's theory, F is a gradient. So if Fermat had tried to do pathwise Stratonovich integration instead of pathwise Ito, there would not have been a paper because it would have been a 3-liner. Right? So, huh? Yes. So as I said, in his case, it's a gradient, right? So the Stratonovich. Well, in dimension 1, everything is a gradient, right? But he's not restricted to dimension 1. But implicitly, the integral that he has in his Ito formula is always of gradient form. So there's no problem. His contribution was sort of to peel off the quadratic variation term, right? And to go from midpoint to left point and to realize, there's a quadratic variation term, and this can all be done in a deterministic fashion. But this one, Fermat cannot do. Uh-huh.
Can we prove this further such continuity?
If you're in dimension 1, there's no problem. Then you will get continuity and subnorm of the right. So then you don't need this whole machinery. Levy area doesn't matter. I mean, you can see it. You can see it here. When you start to feed in, if f happens to be a gradient, then this here would be a second derivative. There's some symmetry going on here, and this will contract against the antisymmetric part, the Levy area, and the Levy area will drop out. Right? So the Levy area, I mean the antisymmetric part, which is the key here, doesn't play a role in the gradient case, and only in the gradient case. Okay, the other thing I wanted to point out is that you have more than just existence of this limit here. You have a very good estimate. So the estimate, and this construction, by the way, this one, the existence of this limit here, this is the prototype of the reconstruction theorem in high-res work. And if you have tried to look at high-res regularity structures, then this is the key result that makes the whole story work. So you should keep this one in mind. So this is an example, if you want. It's an example of high-res reconstruction. Okay. So with some luck, Paul Garcia will get to this on Friday. Okay, the error estimator promised you is the following. If you do, so we have good estimates. And the good estimates of the following form. If you look at this rough integral now, y dx here, and now I don't do it over a big interval. I mean, I haven't specified here. You can think here is a big interval, and here partitions are of this big interval. But of course, I can do the same thing on a small interval. Doesn't matter. So if you do the same thing over a small interval st, then the heuristics over there suggest that this is, to a good approximation, given by the second order expansion here, right? And so there's an estimate that quantifies this. So instead of writing this wiggle here, you should write a minus and then make a bracket here, and then tell me what do we know, right? And what we know here is that this is of order t minus s 3 alpha. And what you should observe here is that 3 alpha is greater than 1, thanks to our key assumption that alpha is greater than a third. So this is really a little o of t minus s, which ultimately is responsible for the convergence of the sum here. Because the little errors, they will evaporate in the limit. So this is a typical rough path estimate. Okay, now, why did I bother to introduce y and y prime here? If you look at the proof of this existence here, there are 2 possible proofs, and I'm not going into details. One is that you just look at dyadic refinement of these partitions and control what's happening in the limit. And the other one goes back to Young's integral, and is based on smart removal of carefully chosen points. They both work. But Gubinelli's observation, it's a very good one, it's had led to a lot of subsequent developments, was to say, well, the fact that the integrand here was of this particular form isn't that important after all. And if you look at the proof, what you need are basically 2 things. And then you do what you do in mathematics. You pick out the properties you like, you make a nice definition, and everything works in this framework. And so Gubinelli's view. By the way, Gubinelli is local. He works in Paris at Dauphine, and he will be here tomorrow, I believe. So he observed that the proof of this, existence of rough integrals relies basically only in 2 ways on the integrand. Namely, you want that y prime is alpha Helder. And the other one is that y is well approximated by x. I mean, this is the intuition behind the whole thing. If y is well approximated by x, you can sort of linearize it, and then you will expect that these iterate integrals pop up. Right? And y is well approximated by x. And let me make this a little bit more quantitative. What you want is that small increments of y behave to first order like small increments of x with a vector here, which is y prime of x. Okay? Okay. And now, again, let me make this a real statement here. What you want is equality here with an error plus error, and this error here should be of order t minus s to the 2 alpha. So it's like a fractional Taylor expansion to order alpha. This tells you what's going on, and then 2 alpha you put in the remainder here. Okay? So these 2 things, you want that y is well approximated by x up to order 2 alpha. Y prime itself needs to be alpha Helder. It's a consequence of these 2 properties that y also is alpha Helder. So you don't have to impose this. And if you look here, I didn't say anything about f, but as you guess, f should be nice enough that everything I tell you works. And if f is such that the derivative of f is Lipschitz, then this will surely be true. And so this is how you end up with some, say, C2 assumption on f for this to work. But let's not, f nice. C2 would do. So at this moment here, you can forget about this here. You can forget about this here, and say I can integrate any y such that there's a y prime. And of course, the construction depends on y prime because you put it in explicitly. So everything depends on everything. But that's a good way to do it, and so it merits a definition. So the good class of rough integrands, if you want, is given by such pairs. Definition, we say that y is controlled by x. The pair y prime is called a controlled rough path. And this y prime here, we call it Gubinelli derivative. Gubinelli derivative. Okay, now you have to be a little bit careful. It's usually clear from the context what it is, because if you start with y equals f of x, then the natural candidate for y prime is the derivative of f evaluated at x. Yeah? But otherwise, you have to be a little bit careful, because in standard calculus, you know that your derivative is well defined if everything is smooth. And if things are rough, maybe there's a sub and super differential, and here it's different. When things are perfectly smooth, you may know nothing about y prime, because you can stuff everything in the remainder, everything is smooth, you don't see it, okay? So the rougher things are, the more you know about y prime. And so this is not just an academic question, what do you know about y prime, or to what extent is it determined? This is actually a key aspect in the rough path proof of Hermander's theorem. And I think Paul will get there on Thursday. Okay, so we talked about integration. The next thing you want to know about is differential equations. And I should look. I have 1 full hour left, is that correct? Yes? Okay. So while I clean the blackboard, I sort of raised the question to the control people here in the audience. If you look at a controlled differential equation, so that's the one thing I can write down now. So think of differential equations. And so there's nothing rough here for the moment. We're looking at an ODE which has the form z dot equals f of z x dot. Now everything is multidimensional, so you should really think of this as the sum of fi z x dot I, right? So this is a typical situation control theory. You have d vector fields, you have a d-dimensional driver, and your robot arm, you can move it around, or whatever example you have in mind. So, and it's a very natural question to understand when is it true that similar inputs will lead to similar outputs. So a natural question here is, when does x close to x tilde imply z? Right? So it's, for the sake of argument, let's say that the starting point here is fixed. Right? So I think it's a very reasonable question. And it's this question, this question is the reason why Terry Lyons called his first book System Control and Rough Path. So I'll clean the blackboard and you you can think about this for a moment. Okay. So the answer I'm heading to will require me to, speak 15 minutes or so about rough differential equations. I mean, there are cheap answers, right? If you're willing to measure the distance of your driving signals in a sufficiently strong metric, such as C1 or Lipschitz, or as a matter of fact, alpha Helder with exponent greater than a half, then you have continuity properties and local Lipschitz estimates. But if you're in any regime where x is sort of rough, and then what I have in mind is this 1/2 minus epsilon Helder regime that we know from Brown motion, then there's no such story, right? Then you can be uniformly close, and the output is all over the place. And if you try to do control theory in that setting, then you should be worried. Okay, rough differential equations. In short, RDEs, rough differential equations. So what we want is a meaning to integral equations. Well, we should be in good shape because we already understand how to integrate. So the meaning of a differential equation should be what you get by its integral formulation, in the same way as you do, Ito equations. When you write dx equals something dp, what you really mean is an integral equation where everything is in terms of well-defined stochastic integrals. Okay, now you can do this, and we'll do it in a second, but there's a sort of a shortcut which is due to Davy, which is actually completely self-contained by definition. This is proposed by Sandy Davy, I think in 05. We say that so Z is a path, dimensions, whatever, these vector fields, if they live on Rn, then Z will be, Rn valued, solves the rough differential equation. So what I'm writing down here is formal. dz equals f of z dx. So as before, this is a rough path. So those of you who have seen the Milstein scheme have an advantage now. Again, you look at your solution over small increments, st here. So you assume you already know where you are at time s, and you look what happens over a small step here. And so the brutal thing to do is sort of follow your nose, Euler scheme, right? So you say, I freeze my position at time s, and then I look at my driving signal, and it tells me to do this. This would be the Euler approximation here. And now you do the next best thing, which is the second order Euler or Milstein approximation. And this would just be plus df at zs f zs. And then you need to feed in the second order iterated integrals. Okay? Everything at time s here. So if you're really honest and you want to write it out as summation over fi, xi, you can amuse yourself with finding the correct order of all the indices, but I mean, you have to do it when you go to a computer, but otherwise it doesn't add much here. And the crucial thing in his definition is, as before, that he says, well, I make this a real requirement. This equals this plus an error estimate, which is of the order we saw before, plus something of order t minus s to the 3 alpha. And since alpha is still alpha Helder, and alpha is still between a third and a half, this is, of course, a little o of t minus s, which is why it's a good estimate. And you can actually, you can hope and you can prove that if you know nothing about rough differential equation, but what I told you today, if you iterate this scheme, so it goes little steps, you iterate, and then you refine, this thing converges. Right? Converges, and the solution will solve this differential equation. Now, there's a different point of view. I mean, this is nice, but it's sort of, it didn't really tell you what is the meaning of this equation. Okay? It's good, but you want to do a little bit better. So the real meaning is to say, well, what do you see from this expansion here? You actually see that z is controlled by x, because everything else is order 2 alpha. This guy is 2 alpha, this is 3 alpha. Right? So this tells you in particular that z is controlled by x, and it tells you that the possible z prime is f of z. Right? So let's observe this. Z is controlled by x with z prime equals f of z. Okay? So now what you would like to do is write this as an integral equation. So now I have to think for a moment, can we understand f z dx here as a rough integral? And now you see why Gubinelli's view is very nice, because if we had stopped the rough integration theory at the level of integrating one forms, so y equals a function of x, then this would be troubling. And in fact, if you read Lyon's original work, he had to come up with a rather cumbersome construction to make sense of this. Right? But here it's very easy, because you already know that z is controlled by x. So guess what? The space of controlled rough paths is stable under composition with nice maps. And f is nice, assumed to be nice. So you expect, and it's a little proposition if you want, that f of z is also a controlled path. In particular, this makes sense as a rough integral. So this is OK. And then the whole equation makes sense as an integral equation. So these are two different point of views, but they're easily seen to be equivalent. Yeah? So now, the best thing about this whole construction is, again, stability. So this is Lyon's famous result. Lyon's 98. Right? So let's see how we phrase it. Okay. So you fix. It doesn't really matter. You can, think of the solution flow and keep your Z0 free, but let's fix it for the sake of argument. So fix Z0, then, well, we need some assumptions on these driving vector fields. So if you think about ODE theory, if you have existence uniqueness, you need, or uniqueness requires 1 degree more frugality than just existence. Right? So here, the integral equation makes sense if f is C2. You can squeeze it a little bit. So 1 degree more you can hope for existence uniqueness, right? And f in C3. Then there exists a unique solution to this rough differential equation. So let's call it Z. And here's the big result. The solution map so the map that associates to the driving signal the output, sometimes it's called Ito map or solution map, or in the rough path community, it's now called the Ito-Lyons map, because there's really no probability here. And this Ito map is now continuous in rough path metrics. Right? What is a rough path metric? Well, we had it on the blackboard 10 minutes ago when I spoke about rough integration. Right? With the tiny difference that here you don't care about your x naught, right? Because the dx will sort of kill any constants, you don't care. Right? It's continuous, and in fact, locally Lipschitz continuous. Right? There's some variations on the theme here. Depends how you define C3 here. If you make sure that f is bounded and derivatives up to order 3 are bounded, so C3b, then you have the global existence of a unique solution. If you drop the boundedness, well, you could explode like in ODE theory, then have here a unique solution up to some explosion time. Okay. Now, this is a good moment to go back to the control theory, and then we can have a quick break. Here, there's nothing rough. I mean, even if all driving signals are smooth, this is a natural question, right? And if you're unwilling to measure this closeness of driving signals in a strong topology, or you're unable to, then the answer to this question is precisely given by Lyons' rough path theory. The right way to measure distances between driving signals is to use rough path metrics. So specifically, I'll write this down and then we can so here's the answer. The answer okay if measure the distance. So I'll first put in the strong topology case. In a strong metric, say alpha Helder with alpha greater than 1/2. Right? So, but it's also okay in alpha between 1/3 and 1/2, provided we use the following metric dx now x minus x. Okay, so this is the one I mean here, alpha Helder, right? But that's not enough. If your alpha is below or equal to 1/2, then you have to feed in the second order iterate integrals. And in this case here, everything is smooth. So you know what you should be looking at. So you can still write it in this form if you wish. But it's understood that these guys here are just classical Riemann Stieltjes integrals. So there's a whole hierarchy of rough path metrics if you want, but I'll stop at level 2. That will tell you when you have a good answer to your question here. Depending of how many iterate integrals you're willing to feed in, you can reduce the alpha Helder exponent as low as you wish. Okay? So it's a very decisive answer, I think, to this control theory question. Okay, quick pause, let's say 3 minutes, and then we talk about stochastic processes, rough paths. Please.
Irritating words.
Oh, thank you. It's okay. It's okay. Pardon? 2 alpha here, sorry. Yes? Okay. Yeah. Well, try in English then. Try in English.
When you write the rough equation,
Yes.
you write y equals f of x x dot. The standard theory is f of x t x dot t.
So, say it again.
F of x t x dot t.
F of x, yes, that's right. Yes.
That's the standard theory.
Yes.
Then you may take it in the vector case, and then it becomes f of x t1 tn, and eventually reach the case y equals f of the path x times x dot t.
You mean the path, the whole path? Yes. That's a good question. So in principle,
Herald has done, right? Herald answered that question.
He writes a lot. I can't read everything he does, but maybe he did. I mean, the intuition is not so hard because although I present everything in finite dimensions, I mean, the sort of analysis that you need is just, you need a norm, a triangle, inequality area, and then, so it works immediately in Banach spaces. Right? So then you can sort of think of the some path-dependent evolutions as a classical differential equations that uses the whole frame as a state space. So that, I think this can be done. But I don't think anyone has, maybe Harald did it. Yeah. Yeah. But that would be a good project. I mean, then you can understand delay equations also in a very unified framework.
So in this case, I think we should have a connection between the Gubinelli derivative and the Jupier derivative. I think it should be the same.
Gubinelli equals De Beer.
Yeah.
Maybe.
A good title.
Yes, a good title for a paper.
It's at least Subriemannian is the relative consequence.
Yeah.
Consequence. But you may extend the Peirce derivative just by writing the fraction.
Okay, interesting.
What shows up
Yeah,
the fraction.
I've got a last question. So, is there a trading interpretation of the additional term, you know, of that one, in order to define the rough path integral? Because these ones look like gamma time variance square or something like this. So my question is, my question is, can you use rough path in order to define a robust hedging strategy?
I'd love to. Now, there are slides from Terry.
Okay.
And as you know, he heads the Mann Institute, so he is under permanent pressure to explain them why rough paths are relevant for finance.
Okay.
So he tried to make a case. I can't say I found it completely convincing, but
No, but
I mean,
let's assume that the market is well defined by a rough path.
yeah.
So okay. So this is my.
I mean, one thing I have not spoken about, and I probably won't, is that once you construct bar motion as a rough path,
Yeah.
and you stick it in this rough integral, then you get the usual.
Yeah.
I mean, it's sort of clear
Yeah,
from
disappear.
yeah.
Yeah.
So if you look at the eta one, this guy here,
Yeah.
the zero mean independent, and so they
Okay.
disappear. If you do the Stotanovich one, then you get some. I mean, you get the correction. I mean, of course you get this one. So maybe the first step would be to give an interpretation, a hedging type interpretation of non-Ito integrals.
Okay.
That you say, well, if you don't have perfect markets, then you can't get rid of the transaction cost, or there's also bid ask, and maybe you can feed it into this correction or something.
Okay.
This was along the lines of the Terry slides, but again, he was very. I mean, you know him, right? He was very loose. But this would be beautiful if that works. But maybe one more thing. I mean, much of the effort that goes into this story is to deal with the multidimensional nature, whereas hedging, even in one dimension, is perfectly non-trivial.
Okay.
So if you understand it well in this setting, maybe Felmer type ideas, then this would be the next step. Okay. I will break my promise here and not go immediately to stochastic processes. And there's one more thing I wanted to tell you about rough differential equations in their own right. So one more thing about RDEs. Okay. So if you take a rough path X and now you perturb just the second order information, right? And so let me make this concrete. So you get another rough path that sort of lives on top of the same underlying path, but sort of we changed the second order information, and let's say we do it in the following way here. For some nice So Lipschitz or 2 alpha Helder would be enough. 2 alpha Helder would do. Okay, so matrix valued path, nice. So the two observations here, this really gives me another rough pass. Why? The chain relation is still okay, because I haven't done anything with the first level, and then putting this one in just means, you know, that I have the usual additivity property of vector increments, and so chain is okay. The other thing I preserve is this 2 alpha Helder condition, because I impose the G is 2 alpha Helder. So this really preserves the class of rough paths that lie on top of a given path X. On the other hand, I can destroy the geometric property. Right? So unless G happens to be of a very particular form, I may lose the geometric property, but that's okay. We've developed this whole level 2 rough integration and differential equations for general rough paths. Geometric was not essential. So let's understand very quickly what happens to the differential equation. So dz equals little f okay. So remember what this meant. I'm being deliberately formal here, so these are heuristics, but you can make everything rigorous along the lines I'm saying here. So okay. It's exactly what we had earlier. This sort of is the Smith-Stein type approximation here. And this means a good estimate, but you know, let's stay on this level here. So now what happens if you change from x to x tilde? Well, this. But this one you can spell out completely because you know what it is. So you can switch back to the old one and instead get a correction term, which is of the form plus df dot f zs, and then you have a g st if you want. So our usual convention here, st. So but now you can go back from this heuristic picture and say, well, so the effect of perturbing the second order information here, this perturbation here, in this precise form, led to an additional drift term in your differential equation of this form here. And since G was assumed to be nice, you can write this out as G dot. And if you want to be sharp and look at 2 alpha, then you have to give this the interpretation of a Young integral, but let's not go there. But the more or less perturbation of the second level leads to a drift appearance in the differential equation. And that is certainly something that control theory people knew in the, I don't know, in the 70s or so. There were many papers by Sussman and students where, I mean, in a pre-rough path language, of course, where such phenomena were studied in a great generality. For us, it also adds something, because sooner or later, we'll take here Brownian motion, and here we have to make up our mind. We can use iterated integrals in Ito sense, or we can use them in Stratonovich sense, and the difference, we know what it is. It's 1/2 times the identity matrix times t minus s. So then you get precisely the Ito Stratonovich correction back. Another example is, you remember this from yesterday, I had this example of a path that spins around very quickly around the origin and converges to the trivial path, but the area, the second level, did not converge. Right? So then you can compare the trivial path, 0, 0 here, with the limit of this spinning path from yesterday, and you get that there's still a limit here, 0, but this here is not 0. Right? So the resulting differential equation, now G will be antisymmetric actually, because you only cooked up area. If you contract this guy here with something antisymmetric, what you get are the Lie brackets of these vector fields. So the punchline is, if you look at the differential equation with two vector fields, and you drive them with this little spinning path, 1 over n times, spin around speed n square, then in the limit, you do not converge to the constant solution that would correspond to a constant driving signal, but instead you will converge to the solution of an ODE that's driven by the Lie bracket of the two vector fields. So it's almost like a little homogenization result. It tells you what's the effective behavior of ODEs in this highly oscillatory limit. Okay, that was my short excursion on these second order phenomena. And now I have 20 minutes or so left for stochastic processes, which of course is nowhere near sufficient, but I'll try. And the most important one is Brown motion. As a rough path, of course, as a rough path. So we take a d-dimensional Brown motion to make it interesting, and a d-dimensional Brownian motion B, dt omega. And as I just said, you can do two things. You can do this B eta, which is this in the eta sense, or you can do it in the Stratonovich sense. And you understand perfectly well the difference between the two. So I apologize to those of you who are not familiar with stochastic integration, but I mean, I don't have the time to give all the background here. So what you want to say is that with probability 1, this gives you a rough path. Because then you have the right to plug everything into this deterministic machinery. And then you should also think about consistency, that what you get is really consistent with the stochastic integrals that you know and the stochastic differential equations that you know. This can be done, and we won't have time for it. But at least I want to show you this theorem. I'll give you a hint about how to go for this, that Brown motion is a rough path, almost surely. And depending if you take Stratonovich or Ito, you will get a geometric one or you won't. It's just life. Also, it's enough to prove it for either one, because you understand that the correction is perfectly nice. It's 1/2 times t minus s times the identity matrix. So as far as the regularity is concerned, I mean, it's fine. Either one will do, and then you have it for both. Okay? So let's go for the Stratonovich. Okay. And why is this true? Now, this geometric point of view that I emphasized earlier today, to think of rough paths as sort of path in G2 in the step 2 nilpotent group, proves to be very handy here, because all we have to do is to show that if we think of this as some, B, right, with values in G2, then we have basically one stochastic process. It's called bold B. It takes values in some metric space. And we want to show it alpha Helder with alpha less than 1/2. Well, you know Kolmogorov's criterion, or some base of Helder embedding, or whatever you prefer. So you know pretty much what you have to do. So, and since everything is Gaussian here, you know it's enough to control the L2 norm, because this will give you the higher moments for free. So it's like a Kolmogorov type argument for Gaussian processes. And so recall the argument for Brown motion. So essentially, it was enough to look at Brownian increments, bt minus bs, look in L2 norm, so over the probability space, of course. So that means the square root of expected value of B ST square. And then Brownian scaling, or it's completely elementary to show that this is like square root of T minus S, right? And then you get the same by Gaussian integrability. You go from second moments to bth moments, and it's still true with a constant that depends on P. And then you use Kolmogorov, and you see you get 1/2 minus Hölder. Okay? So the beauty of this Carnot-Caratidori point of view is that you can do the same. So instead of looking at B, I now look at bold B, and I have to work in this Carnot metric. So I look at DCC B ST, oh no, B S B T L2. So same story, that's the square root of expected value of. And now here it's the Carnot norm, B, bold B, ST. Here I have the Carnot-Caratidori norm square. And then the scaling of Brown motion enhanced with its iterated integrals is precisely consistent with the properties of the Carnot norm. So if you scale B by lambda, then this guy here will scale by lambda square, but the properties of the Carnot norm will make sure that this comes out as a lambda. Right? So you have the precisely same argument. This is like T minus S. Now you may need to know a little bit more about Gaussian integrability of polynomials of Gaussians. But essentially, the same argument works. You can beef this up from L2 to LP. You have this one. And again, you get 1/2 Hölder, 1/2 minus epsilon Hölder. But now, with respect to the Carnot norm, which is exactly what you meant by the alpha Hölder rough path regularity, and you're done. Okay? If you don't like this geometry stuff and you want to do it by hand, then I can promise you, you're in for some work. This was no work. So geometry is useful. Now, a lot of interest. Well, let's recap here. We know Brown motion is a rough path. That means we can put it in this rough integral. We can put it in these rough differential equations. And the reason why this is consistent with the notion of stochastic integration and stochastic differential equations that you know is very simple. Namely, if you go with the eta one and you look at increments, this one has 0 mean, and they're all independent. So expect some cancellation, it just drops out. So effectively, you're looking at the first order left bound approximation, you get eta. And if you do the Stoyanovich one, well, then that's not true. It's not 0 mean, but you know what the mean is. You just put it in by hand, and you will see easily, then you go to the Stoyanovich case. Okay? So you can really do now pathwise, well, to the extent possible, stochastic analysis. Now, the good thing about this approach is you're not restricted to Brown motion anymore, nor are you restricted to semi-martingales, which is basically the natural framework. This is how far you can push these ideas. Right? So stochastic analysis, you start with Brown motion, but then you think harder, and you realize it basically ends at semi-martingales. But here it does not. And the easiest example of a non-semi-martingale is perhaps a fractional Brown motion. And the theory I'm going to tell you about is by no means restricted to this case. But no doubt, fractional Brown motion is a prominent example. It's easy to explain. There's this one parameter called the Hurst parameter where you can turn up and down the regularity. So it's a good one to have in mind. So Gaussian processes. as rough path? Well, I mean, you want to be morally in a world where you have alpha Helder sample paths, right? So we're not being completely general. We cannot be. But let's see what we can have. So the example to have in mind is fractional Brownian motion. Call it BH with Hurst parameter H. Now, as you may know, for H equals 1/2, we're looking at Brownian motion. So that's not the, I mean, we know how to deal with Brownian motion. For H greater than 1/2, it's a simple application of Kolmogorov's criterion. You actually have sample path regularity of something bigger than 1/2. And then you don't need this whole rough path theory because you can do it sort of in a Young setting. You don't need iterated integrals. It's like the level 1 case of rough path theory, if you wish. So here, no need for rough paths. Since sample paths are held of exponent greater 1/2. Right? So the interesting case is less than 1/2. So now we are truly rougher than Brownian motion. Now, what's the main problem here? When you want to write down sort of your natural candidate for the second level information, so in the Brownian case, I mean, this was not a Riemann-Stieltjes integral, right? We needed stochastic integration to come up with this guy. And then with probability 1, it worked. So this is the probability provides this external input that rough path theory lives on. Now here you can try the same thing, but there's no there's right this. I mean, what is this guy? BH is not the same in martingale, so how do you do? So first observation: if you're trying to go for some Stratonovich type theory, so if we try to construct this guy or Brownian fractional Brownian motion enhanced with iterated integrals, if we try to construct this as a geometric rough path, then we don't need to care about the symmetric part of this guy, because the geometric assumption tells us that the symmetric part of this is hardwired to be 1/2 BST tensor squared. Right? So the real problem is the antisymmetric part. Yeah? So enough to understand the antisymmetric part. So let me see. To understand. Right? So the antisymmetric part means you have to look at BH ith component and integrate it against the jth component and then minus the other way around. So what you really need to understand here what we really need to understand is something like this. X dx tilde, where x and x tilde are IID copies of a scalar fractional Brownian motion. If you can do this, then component-wise you can get everything you need. Okay? I mean, we're still at problem 0 here, right? We want to understand what is it. And then at some later stage, we need to check that we have all the properties. Now, the Gen one is easy because if you take the view that we define the rough path really as a path, then the Gen relation is a tautology. The geometric one is also handled because we only construct the anti-symmetric one. The symmetric one, we define it to be what is imposed by the geometric condition. So the real work comes first to define this guy, and second to show that you have this 2 alpha Helder estimate. Okay. Now there's a simple idea, which if you want you can attribute to Ito, which is to say, well, you don't stand a chance to do it deterministically, so you do it stochastically. And I will be a little bit formal now and just tell you an estimate which is valid if everything were smooth. But then if you look at the equation, you realize the right-hand side doesn't depend on the smoothness, and then you do the usual gaming analysis, you approximate with uniform estimates. Okay? So it's a little formal now, but it works. And to phrase it properly, I need to introduce the covariance function, which, of course, in a Gaussian setting is most natural. Right. And of course, you can write it down explicitly in the fractional ground motion case, but it's really a structural assumption on the covariance. Otherwise, everything I'm saying works for Gaussian processes with independent components. It's 0 mean, otherwise you have to adjust it. And this is the key quantity, as you would expect in a Gaussian setting. So if they're IID, then I don't have to introduce R tilde because it's the same. Right? So. And what you do is you look at the object of desire, which is this one here, and look at the L2 norm, or currently. Right. L2 norm square, if you wish. Now let's see if you can get a good estimate. I mean, in the spirit of Ito isometry. And there's one little thing that you can do immediately. And so what's important here, IID stands for independent, identically distributed. So the fact that they're identically distributed is not important, but the independence is crucial here in this argument. So all you do is you say, well, let's do it from 0 to capital T. And there's a little s here. I spell out the square of this integral as a double integral. So now I integrate against, s and t. These are my integration variables. It's a nice double integral. I put the expectation inside. Right? And since they're independent, I can split it up. So I get the expected value of xs times xt, which is just my covariance, against the mixed derivative of r tilde, which happens to be r here. Right? So this is actually nothing else than a double integral, or if you want the integral over the square, that's to right, of rst, and then the mixed derivative of rst. So once more, if you drop the identically distributed property, then you do the same with an r tilde here. So now you do a little research, and you find that this not only looks like a Young integral, but actually it is an instance of a so-called two-dimensional Young integral. And Young integrals basically allow you to play the regularity of one against the other. And so there's an estimate here. So this is a 2D Young estimate. It tells you get an estimate here that only depends on the rectangular variation property of R. So the usually Young inequality would tell you can estimate it by the PQ variation of integrand versus integrator. And the same is true here. So you would have the rho variation here times so again, you could provide it 1 over rho plus 1 over rho tilde. So this is the usual Young condition, and this is what you expect from a Young type estimate. Now here, for simplicity, R equals R tilde, so I can drop this here, this tilde, And here it's the same one, and this just translates to rho less than 2. Okay, now sanity check. How are we doing? We want to do better than in Brownian motion case because we are below Brownian motion in the regularity scale. So where are you in the Brownian motion case? Well, in the Brownian motion case, this guy here is S minimum T. So the mixed derivative, if you want, is the Dirac heterodiagonal, and measures have finite one variation. Rho equals 1. This works for rho less than 2, so we're doing okay. Right? We're going a chunk below Brownian motion here. Now, here comes the tedious part of the story. If you do it with fractional Brownian motion, then you have to find out what is the rectangular rho variation property of the fractional covariance. It's not difficult, but it's a little bit tedious to write it down. And if you're interested, there are some conceptual advances on how you go for it. But in the fractional Brownian motion case, so again, we're interested in h less, let's say less equal 1/2. We don't want to exclude Brownian motion here. You find that rho equals 1 over 2h. Okay? So what does it mean? Well, h equals 1/2 gives you rho equals 1. Okay, that's what we expect. But then you can push it. How far can you push it? Well, critical is rho equals 2. And that corresponds to h equals a quarter. Yeah, so. Okay. So punchline here, you get uniform estimates for fractional Brownian motion as long as you stay above Hurst parameter 1/4. And in fact, you can show that these guys explode in the case of equality. So you get sharp results, which is quite remarkable because a covariance function is not just any function of two variables. It's a very rigid object. And what you used here is a very general estimate on functions of two parameters. So, but it gives you sharp results indeed. Now, once you're here, it's plain sailing, because where do you get this 2 alpha estimate from? Well, in the fractional case, you have scaling, right? So whatever you do here, in the end, the fractional scaling survives, and so you get it out. Instead of the square root of t minus s, as we had earlier, you will get out t minus s to the power h. Same argument works. And then you're still in a Gaussian setting. You go from L2 to LP estimates, and you conclude that you get the Hölderlin regularity on the rough path level that you expect, which is h minus epsilon. So it really works in a very general Gaussian setting. Maybe one more word. If you're interested to go all the way down to h², then the regularity will also be down there, around a quarter. Whereas the whole story that we developed, we always did alpha greater a third. There's no contradiction here. If you really want to go down there, then you have to live with the fact that you have to feed in and understand the third iterated integral. So it's a little tedious, but can be done, and there are all the details in my book with Victoire. But if you want to apply what you've seen, then you should take h greater than a third. And then everything that we did applies. But otherwise, it still works, but what I've shown you is not sufficient. You have to beef up your understanding about rough path theory a little bit. Right, I have 1 minute left. I was tempted to tell you a little bit about Levy processes as rough path, but I don't think time permits. But if you're interested in this, then look out for the archive. I hope to put it up there in a week or so. The reason it's interesting, I believe, is the following. So the main criticism that I've encountered over the last 10 years or so working in this field is that it doesn't deal with discontinuous processes. And so if you do finance or other stochastic modeling things, then there are jumps. There's no doubt that jumps are important. And the theory as developed doesn't deal with jumps. Everything is continuous. I mean, Hölder is, So you have to switch to a p-variation setting, which is already there in Lyon's original work. But even there, he talked about continuous path or rough paths of finite p-variation, and it's used. So the theories are not, it's not a special case or a tiny generalization, but it does work. So there's a theory, it's a notion of a Cadillac rough path. You can turn Levy processes and more general jump diffusions into Cadillac rough paths. The interesting structural conditions like some Blumenthal-Guettor index, where you try to understand how the Levy measure on the Lie group integrates the Carnot metric near the unit element, which power. And so there's a rich theory on Levy Cadillac rough paths to be out soon now. And the last thing someone asked me to is as references. I mean, you know, Google is your best friend as usual. But there are a few books that I should definitely mention. I mean, the most important one is probably Lyon's original article in 98. And of course, it's in many aspects it's outdated. There are much slicker arguments, but it's also impressive to see the vision that he had. I mean, there's a list of 10 possible applications of rough path theory in the introduction of his article, and every single one became true. And the last one, if, you know, with little goodwill, you can say this is the work that Martin Heyer got his Fields Medal for. It's in the introduction of his 98 paper. Now, there's some floor notes, and these are by, I think, 007 or maybe 8. Also by Terry Lyons, jointly written with Michael Caruana and Thierry Levy. Then there's the book with Victoire, Friz, Victoire. This is Cambridge University Press in 10. So some flow notes there, Springer. And so if you want to learn about semi-martingales and Markov diffusions as rough paths, you know, this has been systematically developed in this book here, as well as the general theory of you know, geometric rough paths. And last not least, there's this book with Martin Heyer, and that's 2014. And so this one was, you know, was really a monograph. I mean, we put in this best estimates because you never know when you need them. But this here is a textbook. So this was designed to be easy reading, minus perhaps the last 3 chapters on regularity structures. They're a little tougher. But the first part here definitely, I mean, if you have a 3-hour train ride, then, you know, it will make a pleasant reading, I hope. And as far as I'm concerned, that's it. Paul Garcia will take over. I'm happy to answer any questions. Thank you very much for your attention.
So we take out Peter Friz, and our stochastic week will continue this afternoon with a seminar on Isaac to Z. Then tomorrow with the thematic day, and then there are 2 lectures. So